In this video class, we are going to find out the effective capacitance when the different capacitors are connected combined in a parallel way. So the parallel combination is shown in this given figure. In parallel combination of capacitors, the first plate of all the capacitors are connected to one point A and the second plate of each are connected to another point B, A as well as B. One plate to A and the other plate to B. So this is the figure. In the given figure, three capacitors of capacitance values C1, C2 and C3 respectively are joined in a parallel way. So you can see charge Q is going through different capacitors, but in this figure, apart from series combination, here I can say the feature like this. The charge Q is being distributed among all the capacitors. That means when a charge Q is going to three capacitors, it will be divided equally among the capacitors. So Q will be distributed to C1, C2 and C3 respectively according to their capacitance values. But in series combination, it was not like that. In series combination, the charge Q was constant through all the capacitors, but here the charge Q is being distributed among all the capacitors. Since there are three capacitors available in this figure, so through C1 I can say the charge going through C1 is Q1, through C2 the charge going is Q2 and through C3 the charge going will be Q3. So it will be easier for you to understand. So Q1 charge is going through C1 capacitor, Q2 is going through C2 capacitor, Q3 is going through C3 capacitor. So what will be the total charge value? Q1 plus Q2 plus Q3 will give you the total charge value Q. That means the charge is being distributed among all the capacitors. If there are 4 capacitors, then it will be Q1 plus Q2 plus Q3 plus Q4 will be equal to the total charge Q. Like that, n capacitors are there. Suppose if there are n capacitors, then the charge value, total charge value will be Q1 plus Q2 plus etc. plus Qn will be given by Q total charge. Like that, the charge is distributed among all the capacitors here. But the second feature is like this. In series combination, when we were studying in the last day, in series combination, apart from the charge, there the potential difference was a varying term, right? There I wrote like this: V1 plus V2 plus V3 was given by the total potential, that was V. But here, since the charge is a varying term, but here through capacitors the electric potential will be a constant term. So all the capacitors, through all the capacitors, the electric potential difference between the 2 points will remain the same. The reason behind the feature is, as all the 3 capacitors are joined between the same points, that is A and B, 2 ends only, A and B, hence potential difference V between the plates of each capacitor remains same and equal to the applied voltage, that is V. So since they are connected across equal points, so all the capacitors C1, C2 and C3 are connected towards the equal ends A as well as B. That's why the potential difference across those points are always remaining the same. That's why the potential difference across C1, C2 and C3 will be same, that is V. So here only Q is changing, but the potential difference V will remain the same. Q total charge will be given by Q1 plus Q2 plus Q3, but potential difference will be same in parallel combination of capacitors. Now we are beginning the derivation. We start with the previous equation, that is Q1 plus Q2 plus Q3 equals total charge, that is Q. Now for Q1, Q2 and Q3 we are going to substitute a new relation. Relation already you know, the relation connecting capacitance C, electric potential difference V as well as charge Q. So Q equals Q1 plus Q2 plus Q3. Instead of Q, we are going to substitute the relation. So you know well that what is the equation for capacitance? Capacitance C equals Q divided by V. Now we want to find out the equation for Q. That is what it is given in this equation, right? Q equals Q1 plus Q2 plus Q3. So we have to find out the equation for Q. Q will be equal to CV from the above equation. So we can substitute instead of Q this equation, Q equals CV. So what is the value for Q1, Q2, Q3? It will come to your mind directly now itself. So what will be the equation for Q1? Q1 will be equal to C1 into V. Why it is V? Because potential difference V will be same everywhere. Across all the capacitors, electric potential difference V will remain the same. So only C1 capacitance will change. What will be Q2? Q2 will be equal to C2 into V. And what will be Q3? Q3 will be equal to C3 into V. Look here, V remains same everywhere. So after getting these equations, we can substitute in the given equation, that is Q equals Q1 plus Q2 plus Q3. Instead of those values, we can substitute CV, C1V plus C2V plus C3V. So CV will be equal to C1V plus C2V plus C3V. We are taking the values from left side. So here you can see the V is a common term. So CV will be equal to, V can be taken outside the bracket. CV will be equal to V into C1 plus C2 plus C3. CV equals V into C1 plus C2 plus C3. So next step will be, of course, V and V will be cancelled. V in the LHS, V in the RHS is being cancelled each other. So the remaining term, here you can see yesterday itself we have seen C in the LHS side is the total capacitance value. Total capacitance, or other name, effective capacitance, or equivalent capacitance, by any name you can call it. So C effective or C total or C equivalent will be equal to the remaining term. They are C1 plus C2 plus C3. This is the final answer for parallel combination of capacitors. The capacitance, the equivalent capacitance by a parallel combination of capacitors, we will get it like this. C equivalent or C total will be equal to C1 plus C2 plus C3. So from this equation we can find out, in parallel combination of capacitors, the equivalent capacitance will be equal to the sum of the individual available capacitance values. So C1 plus C2 plus C3 plus up to Cn, you can write the value. So the total capacitance is equal to the sum of the individual capacitance. Let's go for a numerical problem. So two capacitors are connected to a battery. Two capacitance value I will give, they are 2 microfarad as well as 3 microfarad I am giving here. So they are connected in a parallel way. What will be the effective or resultant capacitance here? That is the question. So you know the equation, C total or C equivalent will be equal to the sum of the individual capacitance C1 plus C2. Answer will be 2 plus 3, 5 microfarad. This is the final answer for C total. So here it is clear that the equivalent capacitance will be always greater than the largest individual capacitance in the combination. But yesterday it was just opposite to this definition, right? So the equivalent capacitance is greater than the largest individual capacitance in the combination, 2 and 3. But the total capacitance here I got it as 5 microfarad. So always the total capacitance will be a higher value. Hence the parallel combination of capacitors should be used when the capacitance is to be increased. Okay, that is the final inference that I can get from this parallel combination. Thank you, students.